In this video, I'm going to be talking about zeros of a function, and more specifically, zeros of polynomial functions. Zeros are just a fancy word for x-intercepts or roots. Those are all talking about the same thing. Where does our graph cross the x-axis? What value is that crossing happening at? Those are zeros. And I could show you exactly why they're called zeros. We'll get into that when we start factoring and solving. But let's just look at a graph to start things off here. If you have a graphing calculator handy, that might be nice to use. You can follow along a lot faster here. If you need to pause the videos, go ahead and do so. For the sake of time, I've done everything ahead of time, so I'm going to be moving rather quickly here. If I want to graph this function right here, type this into your calculator and see what happens. You can look at it that way, but I've also described an in-behavior option where you can sketch these graphs without even looking at your calculator. If I look at my leading coefficient, it's even, so I know that my graph is going to be moving up from left to right. I know that because my degree or power here is an odd power, I'm going to have a little bump in it. So I'm going to have something that looks like this. And exactly where it is on the graph is what you need your calculator for in order to sketch it. There are ways to do it by hand, it just takes a lot longer. So for the sake of time, there's what this function is going to look like graphed. Just a little sketch there. This point right here where the graph crosses the x-axis, normally called an x-intercept, but it's also more fancily called a zero because it's where our function is zero, where our output is zero. So you might see a statement that says this: the output of our function is zero right here. The y value is zero. And that's why they're called zeros, where the output is a zero, but more commonly just called an x-intercept. Alright, so let's look at another graph here. See if you can kind of get the hang of it. Let's choose a different function now. This one is going to be x to the fourth plus 3x cubed. Now again, I can sketch it by checking out my leading coefficient. It's positive, so I know it's going to be opening up. But this is even, this degree is even, so I know it's going to be similar to a parabola, but with a little bump in it. So it's opening up with a little bump in it. It's probably going to look something like that. Now it could look slightly different. This is just the basic idea of what it's going to look like. If you actually type this into the calculator, you see something that looks more like that, I guess. I mean, it's not completely accurate there, but you know, it's a little tilted. And so this graph will have how many zeros? Well, if we look, it crosses it here, there's 1 0, and it crosses it there, there's another 0. So 2 zeros. And you can use your calculator, you can actually trace the graph, come up with the actual zeros there. I actually pretty far off there. What the graph really does is got a 0 at -3 and at 0, I think, if you look on a graph. So my apologies, it's kind of more like that. I'll show you exactly how to find the actual zeros coming up next here. So always just have a basic idea of what your graph is going to look like by using those in-behavior methods. And if you don't know what I'm talking about, check out that video I made on in-behavior or look in your book. But there is a more accurate way to find the zeros aside from just looking at your calculator. Let's use another example here. Do x cubed minus x squared minus 2x. So we can factor polynomials and solve for our x. That's another way to find x-intercepts. And that would actually give you the real value of your 0, or the real value of your x-intercept. So let's do factoring here, and then we'll look at the graph just to double check. One technique to factor polynomials is called the grouping method, or we could also use greatest common factor. For this example, I would say that because they each have a x in each of the terms, we could take that out and rewrite what's left over, and then that makes it a lot easier. So now we just got a little quadratic here. Hopefully we can factor using some quadratic method. And then I'm going to use 2 sets of parentheses here. If I have factors of -2 that add up to -1, well, -2 and +1, fill those, and we're basically done now. Now we just got to know where to look. So we remember we want our output to be 0. So if we set it equal to 0, we can solve. If I cover up this much, and I'm just looking right here, what value would cause this entire thing to become 0? What could I plug in there? Well, that hopefully is an easy answer. It's just 0. If I plug in 0 here, the whole thing becomes 0. I get an output of 0. So there's one option for x. But we also have these other options. So what could I plug in right here to make the whole thing 0? Well, if I made this equal to 0 here, then multiplying by 0 would cause everything to become 0. So if I plug in a +2 there, 2 minus 2 would be 0, the whole thing would become 0, we get an output of 0. So 2 is another value. If I do the same thing over here, what could I plug in here to make the whole thing 0? Well, I could plug in -1, that would cause the whole thing to equal 0. If you can't do that in your head, you can set each of these values inside the parentheses equal to 0 and solve for x. So for example, if I did x minus 2 equals 0 and I solve for x, well, I would add 2 to both sides and you would get x is 2. So that's how I came up with that inside my head. But really it's just the opposite of what's in your parentheses here. The opposite of -2 is +2. And that's a little shortcut you could use. The last thing we're going to do is we're going to describe something called the multiplicity of each 0. So how many times do these zeros actually occur? Which is something that's kind of brand new. First, let me get a graph going here. If I were to graph that function there, I would get something that looks like this, and I'll try and draw it accurately here. So use your calculator, and it does something like that. So what are my zeros here? Well, it crosses right here at -1. Crosses at -1. It crosses again at 0. And it crosses again right here at +2. And that is what we described, or what we found out when we factored 0, 2, and -1. There they are. So again, zeros are x-intercepts. Now the last thing to do is to describe the multiplicity. Multiplicities. How many times these zeros occur? Well, if the graph crosses the x-axis fully, like it goes all the way across it before it turns around and comes back the other way, if it crosses the x-axis, the multiplicity is 1. If it touches, and we'll look at this example next, if it touches and then turns around, then our multiplicity is going to be 2. I'm going to show you another way that we can find that out here. When we factored, if we look above here at our exponents, or our degrees, or our powers here, this was implied that it was a 1 there. There's also another invisible 1 there, and another invisible 1 there. That's another way to look for your multiplicity. Multiplicity is always the degree at which your zeros happen. So they're all an imaginary 1 there, a degree of 1. So the multiplicity is all 1. And again, you can double check that on the graph, because at each of these zeros the graph crossed it, so our multiplicity was 1. Let's look at one where our multiplicity is actually 2. What does the graph look like? here's another function. If we could factor this and set it equal to 0, we could describe the values of the zeros, or the x-intercepts. Is there something that each of these terms have that we could take out, a greatest common factor here? Well, they all are multiples of 3, and they all have an x in it. So if we take out a 3x, let's see if what we got left over becomes a lot easier to work with. That would be x to the third minus 2x squared minus 4x plus 8. Still not too easy to work with there. Is there anything else we could do? Well, go back to that grouping method. If you don't know how to factor using the grouping method, check out that video, factoring polynomials. So if we just look at these first two terms here, what could we take out of those first two? Well, we could take out an x squared, and that would leave behind an x minus 2. And then if I focus on these last two terms, I could take out a negative 2, and that would leave behind an x. Sorry, don't take out a 2, that would be silly. Take out a 4, that's what I meant. A negative 4, that would leave behind x minus 2. And as long as we get the same thing in both of these little groups, we know that we did our grouping method correctly, and we are allowed to rewrite it like so here. 3x, I'm going to put my x squared and my negative 4 in one set of parentheses, and then I'm going to put my x minus 2 in the other set, and I have regrouped correctly. Now we notice that we have a difference of squares, so I got to refactor that. Got x minus 2 and an x plus 2 and another x minus 2. Now we factored all the way down, and we can look at our zeros. So I'm going to do one more thing here. Because I have two sets of x minus 2, I'm going to rewrite that using an exponent. So if I had 3x and x minus 2 squared, that would be both of those written together, and then that would be my most simplest way of writing it. And it's also the most helpful when we describe our multiplicity. So the zeros here, what would make this 0 would be 0. What would make this 0 would be a positive 2. And what would make this 0 would be a negative 2. And if I look at my degrees, I could describe the multiplicity. Because this is implied that it's 1, I have a multiplicity of 1. It's going to cross the x-axis at 0. Right here, because I have a degree of 2, that means my multiplicity is 2. So we're going to see on the graph that our line is going to just touch the x-axis at 2 and then turn around. And then at negative 2 here, it's going to have a multiplicity of 1 again. Right there is implied that it's a 1. So let's look at the graph. If you plug this into your graphing calculator, you can check it out with me. So when we look at the graph, we notice that it crosses right here in behaviors going up there. It's going to cross at 0, and then it's going to just touch it right there at 2 and go back up. It's kind of a messy graph, but it's basically the idea. So at negative 2, it crossed it, so that was a multiplicity of 1. At 0, it crossed it, so that was a multiplicity of 1. And then at 2, at positive 2, it just touched it and turned around, so that was our multiplicity of 2. Alright, so again, zeros are just x-intercepts. You can find those by looking at your graph or by factoring and solving for x. And then describing the multiplicity of each 0, either it crosses and has a multiplicity of 1, or your degree is 1, or it touches and turns around, which is a multiplicity of 2, and when you're factoring, that would be a degree of 2. Alright, so good luck coming up with zeros of polynomial functions and describing their multiplicity.